with energy, getting it from the place that you stored it to the place you want to use it is very important. Whether it's piping or charging or transmitting or refueling, it's always key to the process. And that's exactly what we're going to be talking about today on Hyfindr Tech Talks, to a gentleman who's actually a boat builder who went on to electrify boats, then refueling fighter jets, and now works for Fuel Cell Systems, a UK-based company that provides fuel cell systems and does refueling. I'm very, very pleased indeed to welcome Sam Whitworth to Hyfindr Tech Talks. Welcome, Sam.
It's a pleasure. Thank you for having me.
Sam, so what is a hydrogen refueling station?
At its most simple, all a hydrogen refueling station is the process equipment to get the hydrogen from where you've stored it into the target vehicle that's going to be using the hydrogen. So it's very similar to your petrol or diesel forecourt refueling station. It's taking the energy carrier and putting it into the vehicle that's going to use it.
Mm-hmm. I'm sure you could speak volumes of this, but like, what makes it particularly difficult or easy building a hydrogen refueling station?
So I think there are two challenges really. Firstly, hydrogen is the smallest element on Earth, so it's very easy. It finds ways to escape. So you need systems which have very high levels of engineering tolerance to prevent it escaping. Mm-hmm. It is also quite a unique element and molecule in that it experiences the reverse Joule-Thomson effect. What that means is when you're refueling, where you might let a normal gas expand, it would lose heat. Hydrogen gains heat and it heats up. And that's one of the key challenges with designing and building hydrogen refueling stations.
Mm-hmm. So that means when it expands, it heats up. Is that correct?
Correct, yeah. Its temperature increases, which is the opposite to just about every other gas.
All right, exactly, because that's normally the opposite. And you have an image here of the setup of a refueling station.
Absolutely. And this really is on screen to show you the key parts. So the first thing you have is the tube trailer. That is supplying the gas to the site. So you have to get the hydrogen to the site. Now that could be a pipeline, it could be an electrolyzer, but in this example, it's a tube trailer. You then have a system which we call Hyfindr, and that is our compression and gas management system. What that does, it takes the gas from the tube trailer and it compresses it into high pressure storage on site. So on this example, you can see there's hydrogen storage at 500 bar. Mm-hmm. You then have cooling plants. You need to cool the hydrogen in order to refuel it quickly into vehicles. And the last image on the screen is something which we call our high flow product, and that is the dispenser. And that's what people would be very used to using. It's a hose with a fitting on the end that you plug into your vehicle, and that controls the refueling of the hydrogen from the station into the vehicle. So this really is a simplified diagram of a hydrogen refueling station.
And just again, you need the cooling because when hydrogen expands, it heats up. And where does it expand in this setup?
Yeah, it's a great question. So you need the cooling if you want to refuel quickly. And a key part of our conversation today really is how quickly do we need to refuel? Because it's very easy to get carried away and go quicker and quicker, but that needs more and more energy. Just to answer your question on where does the hydrogen expand to, if you've stored gas on your site at 500 bar and you come in with your car and the tank's empty, it's only at 50 bar, the gas is expanding into the tank. So it's going from 500 bar to 50 bar. And as your vehicle tank is being filled up, that gas is expanding less and less. But initially, there's a lot of expansion as it's going from high pressure to much lower pressure in the initial refueling of the vehicle.
Okay, so you would need to cool it a lot so it doesn't heat up inside the vehicle that much.
If you want to refuel quickly, you can refuel perfectly safely with absolutely no chilling. You just have to do it that little bit slower.
Okay, so please take us through what you. I think there's more to it than that. So let's go step by step into the kinds of refueling and things.
Sure. So just before we move on, I wanted just to show you the different scales of refueling. So we showed you a very simple site. And this image on screen now is just showing you what happens when you go from running 10 lorries to 30, 40, 50 lorries. And the simple answer is it's exactly the same. There's just more of each unit of equipment. So more compressors, more storage, more dispensers.
Understood.
To go into refueling, what types of refueling are there?
Okay.
So today we're going to focus on Cascade refueling. But before we go there, I wanted just to acknowledge there are several ways of getting hydrogen from your station into the vehicle. The most simple is decant refueling, and that is where you have a high source pressure and you decant it into the vehicle. The issue with that being you may only get 1 or 2 refuels before your source pressure has really been depleted. The second is direct compression, and that is where instead of compressing the hydrogen into storage, you compress it directly into the vehicle tank. That really you'll only see in experimental setups. It's not compliant with the refueling protocols that you need to refuel the public on forecourts. And the third method is where you go for cascade refueling, and that's what we're going to be talking about today. And cascade refueling is where you take multiple source pressures and you cascade it into your target vehicle.
Okay, I think you need to explain it a little bit more, but just for me, the first one is like where you had like what we see on, when you have to pressurize container and you want to fill in balloons. So I think that's like on a kid's birthday, you have a pressurized container and you fill several balloons. I think the second one,
Absolutely.
Is it correct to say it's like pumping your bicycle tire with the compressor? You're literally always feeding in that. Okay, then I'll leave you to explain the third one.
They're great examples. Yeah, certainly the can is very much like filling a balloon, and yes, the bike tire, pumping up your bike tire. That is the equivalent of your vehicle tank. Cascade refueling really is the big one to talk about today, and I've got a couple of animations to help with that. What we have here, and you can see, is to start with our high cube refueler takes gas from a tube trailer, the source pressure, and we make use of that. We don't want to compress gas we don't need to. So if our tube trailer's got high pressure gas in it, we take it directly from the tube trailer and we put it into the vehicle. And in this example, that gets the vehicle up to 100 bar. The second thing that happens when we run out of pressure in the tube trailer, we move on to storage bank 1. And in this example, storage bank 1 is a 500 bar. And we take that gas from 500 bar via our refueler and we put it into the vehicle. And in this example, it gets us to 400 bar. And finally, you go to a high pressure source. So in this example, that's 850 bar. And that 850 bar source takes the vehicle from whatever pressure it was, in this example, 400 bar, to the 700 bar end pressure. So what you see in this example is that we're working up the pressure gradients. The key thing there is we're only compressing what we have to. If we used 1,000 bar gas to refuel a 50 bar tank, we've pumped that gas all the way up to 1,000 bar, and we've had to give all that pressure away. We've had to give away, we're only using 1/20th of the pressure. 19 units of pressure we're giving away in that example. When you
so essentially, you would need to on site, you would roll in the trailer, and then you would fill up those storage banks and have those at your disposal, so that when the refueling vehicle comes, you use them in the sequence as you've described, right?
Yes, and the next graphic really is a truer representation. So what happens is you connect your tube trailer to the system, and the system decides what gas from that tube trailer to use for replenishing the on-site storage, and what gas to send directly to the vehicle. Our mantra is very much only compress what you need to. Just because you've got lots of storage and just because you've got big compressors, every time you turn them on, you're using money, and ultimately you're costing money. You're using energy, you're costing money. So we want to be more intelligent about how we control our system. And in this example, there is gas going directly from the tube trailer to the vehicle, and there's gas going back out to the storage banks via compression. And in a system like this, one high fleet could power multiple high flow dispensers. So this picture gets maybe more complex, but you can see the flow of gas through the system.
Got it. Okay.
Once we've got our system designed, we then need to control the refueling, and that's what we're going to talk about now. So this table looks intimidating, but I'm going to talk through it. There's nothing too scary in here. So this is a direct lookup table from J2601, and I'm sure everybody's heard of J2601. Is maybe a little bit
it's the most known thing in the world. What on earth is J2601?
And I don't know why it's called J2601, but that is the label it has, and it is a standard from the Society of Automotive Engineers, so SAE. And it's very much like the standard that controls an ISOFIX seat you might use for your children. The whole idea is any station can communicate with any vehicle, and because we conform to this standard, it's going to behave predictably. So it's no different to standards on headlights or seat belts or the bolting patterns on car wheels. It's a standard that automotive engineers use when developing the vehicle or the equipment to service the vehicle, in this case, refueling.
Actually, I must say, the Society of Automotive Engineers, I know that is over 100 years old, and it has gone right all through the ages of the automobile, and has always sort of brought these things into place to make this industry or this means of transport more successful and safe, obviously. So probably they put this together also for the refueling.
Absolutely,
in that sense.
Yeah. And it's a continual piece of work. So
Right.
at the moment there are several standards under J2601, and there are more in the works. And the whole idea of those are to allow a wider variety of refueling techniques, with the fundamental number one priority being making sure it's safe and predictable.
Understood.
If I explain this table, the first thing I've highlighted here is the title. And that gives us a lot of information. So we can see from this, it's H70. That means it's a 700 bar vehicle. We can see it's T40. That means the hydrogen is pre-chilled to minus 40 degrees before it goes into the vehicle. We can see it's a category D vehicle. That means the tank is bigger than 250 liters and it stores more than 10 kilograms of hydrogen. And we can see it has communications. And that means there's infrared communications between the vehicle and the refueling station. And that's exchanging information about temperature and pressure and the vehicle status and the refueler status. So they're communicating.
Okay, so that is the infrared thing in the nozzle. That is
the ring on the outside of the nozzle.
Yeah, exactly. So there's so I think that's something very unique about the hydrogen situation, that the dispense is actually talking to the vehicle, as you know. So they're busy having a conversation about these values.
And it enables some of the more efficient protocols to be enacted when you have that communication.
Right.
Just to explain a bit more about what matters in a J2601 lookup table, the first thing we're going to look at is temperature. So this highlighted cell is the ambient temperature, and that has a very large effect on refueling. You can see on a cool day, you can refuel at nearly 20 megapascals a minute. On a hot day, you can only refuel at 7.5 megapascals a minute. If you're above 50 degrees, you can't refuel at all. So ambient temperature has a huge...
Where do you look that up? 7.5 megapascals a minute. Where do you see that?
If you can see my cursor, I've got 7.6.
Yes.
But I'm going to talk now a little bit about average pressure ramp rate. It's a good thing to move on to. Again, I get asked so many times, why does it take the same amount of time to refuel a car as it does a lorry or a bus? And it's all to do with APRR, average pressure ramp rate. So what this is saying is, if it's 50 degrees centigrade outside, the pressure inside the vehicle tank can increase by 7.6 megapascals a minute. Now, to convert that to bar, it's 10 to 1, so 76 bar per minute.
Okay.
So the average pressure ramp rate is hugely impacted by the ambient temperature on the day of the refueling. And a refueling station that's going to maybe work in Finland would have different performance and cooling characteristics to maybe something that's going to be deployed in the south of Italy, because we're expecting in very different environments.
So the higher the temperature, the less the rate. Is that correct?
The more slowly you have to refuel, because
the more slowly, exactly. So you can literally fill that vehicle faster on the North Pole than you would on a hot day in Dubai.
Yes, absolutely correct.
Yes. Okay. Yeah.
The second thing, or the third thing we're going to look at is the target pressure. So we talk about 700 bar refueling. Very rarely do you fill a vehicle to 700 bar. The 700 bar is the reference pressure at rest at 15 degrees Celsius. So what you have to do when you're refueling is you have to account for the temperature on the day and the heat gain in the tank. And to give you an example here, we're going to pick a vehicle that comes in maybe 1/3 full, so it's got 150 bar of pressure in it. It's a 25 degree Celsius day. We actually fill that vehicle to 860 bar, 86 megapascals. So you can see the difference between, although we nominally say 700 bar refueling, we have to refuel 160 bar beyond 700 bar, so that at 15 degrees at rest, that pressure will drop back. So you can see the difference in pressure that the environment is able to cause. It's quite extreme, actually, and something you have to be very mindful.
That is. And the top line there is the temperature of the tank of the vehicle.
The initial pressure of the tank. So
the initial pressure of the tank. Okay, initial
if
pressure.
You're all the way to the right, the vehicle's full. It doesn't need any fuel. If you're all the way to the left, the vehicle's empty. It's got no fuel in it.
Okay. So you are only interested in the initial pressure. Well, and what about the current pressure during the
current
process?
pressure is what we monitor to control refueling.
Right.
So we are controlling the rate at which the pressure increases. So if we know the start pressure is, say, 100 bar, and we know that we can refuel at 50 bar per minute, we know after 1 minute of refueling, we should be at 150 bar. So we're constantly monitoring that to make sure that the pressure gain is compliant with this table.
Okay, understood. Okay.
Now, what does this all mean? I've dived into J2601 and sort of taking you into the world of maybe some of the data. It means this. So here we have two examples. On the left, we have the Alpine hydrogen hypercar. This is actually a combustion engine hypercar. And this was being refueled at the Goodwood Festival of Speed. This vehicle was refueled in the middle of summer without any cooling whatsoever. So we can do this. We just have to be mindful of how fast we're doing it and how much energy we need. This setup was in the middle of the field, so there's no way you could get huge power connections and chillers to it. We had to do it differently. The image on the right is actually at Schiphol Airport, and this is the Toyota Hydrogen Hilux, and that's being refueled as part of a trial. It was being used for bird scaring on the end of the runway, so the vehicle was going runway and chasing away birds. Again, that was refueled with absolutely no chilling. So by looking at the lookup tables and by building the right protocols, you can do this with minimum energy requirements. You can go fast, but you can also go slower and use a lot less energy. So to bring these back,
show us the example, because I have a question. Because if it was a race car, I mean, obviously time sometimes does play a role in how fast you feel. But please let's have a look at the example, and then maybe we can look at that.
Don't be alarmed by the amount of numbers on the screen here. There's only a couple I really want to focus on. The first two parts are directly from J2601. So we're referencing the temperature and we're referencing the pressure ramp rate.
Right.
What we have then done is said, okay, what does that mean? So if I've got a heavy goods vehicle, these numbers tell me how many grams a second of hydrogen need to go into the vehicle tank to make that pressure ramp rate. The second set of numbers, so that's on a 50 kilogram tank, so quite a large hydrogen tank. The second set of numbers are for a car or a van with a 7 kilogram tank. And what you can see is it's a much lower mass flow rate. So the pressure ramp rate stays the same, but the mass of hydrogen entering the vehicle every second is lower. Now, I'm just going to try and make that a bit more real in terms of refueling time, because I think this will answer your question on race cars.
Right.
So in this worked example, the first thing I want to look at is the car. So if we refuel a car at 30 grams a second, we can see it takes 3.9 minutes, just under 4 minutes. To do that at that speed, we must chill the hydrogen to minus 40 degrees. That's what J2601 tells us. And minus 40 degrees at 30 grams a second requires 28 kilowatts of cooling power. So if you think of an average industrial unit, they may have a power connection of somewhere between 60 to 80 kilowatts. So this system would be something that you could deploy very easily without large-scale grid upgrade. You don't need to put new power supplies in.
So if we can refuel the car in 3.9 minutes using that mass flow rate, which you got from the table.
Correct.
And you would need 28 kilowatt of cooling. You would need some cooling. Yeah. Okay.
Yes, you would need some cooling. So to
is
do
there
that
always some cooling?
No. So if you wanted to refuel that vehicle without cooling,
Yeah.
that might take somewhere between 15 to 30 minutes, depending on the temperature of the day.
Okay. Right.
So we're not saying you don't need any cooling whatsoever.
Yeah.
What we're saying is, let's think about what we actually need. So 4 minutes to refuel a car is very good. You don't need to refuel a car any quicker. To refuel a car in 1 minute, you need 110 kilowatts. And that means you need to spend more money on your chillers, you need more power, your grid connection needs to be larger. So what we're saying to the industry is, let's base it on requirements. Instead of getting fixated on a mass flow rate, why don't we base it on what the user needs? So instead of saying, I want 200 grams a second, we want to say, we need to refuel 20 buses within 2 hours, and we can work out the best way to do that.
Understood.
Now, if we apply this example to a heavy goods vehicle, we can see that at one end, the extreme, we could refuel our heavy goods vehicle in 3.1 minutes, extremely fast. But to do that, we need 240 kilowatts, quarter of a megawatt of power. Now, we don't need that power for very long. We need it for 3 minutes. But we need a very high capacity supply to cool that hydrogen. And that's what I'm saying today. That's my key message today is nobody needs to refuel a heavy goods vehicle in 3 minutes. When the drivers stop, they're due their mandatory breaks. They're going to be stationary for a period of time. The beauty of hydrogen refueling is you can plug it in and you can go and have a coffee and use the facilities and have a break and a sandwich, because the machine will look after itself.
So
Now, we don't want hydrogen refueling to take hours, but actually, if we look at this example here, a diesel heavy goods vehicle, industry data. Now, people will dispute this. Some can be quicker, some can be slower, but we've seen some industry data that says 15 to 30 minutes. If we look at refueling in 15 minutes or less, we can see 60 grams a second works. That does 14 minutes, and it only requires 38 kilowatts, well below that 60 to 80 kilowatts that most industrial sites will have available.
So just coming back to your original statement, you said that you can literally plug that in. So I'm just imagining that earlier slide you showed, but you could have several outlets, and then you could plug it in and then leave the vehicle to be refilling itself. It'll take 15, 20, 30 minutes, whatever, and you could walk away. But can you not do the same with diesel? I mean, can you walk away if you say diesel takes 15 to 30 minutes? Can you walk away with diesel?
The big difference between hydrogen refueling and diesel refueling is hydrogen is a closed system. There is no open canister. So when you connect a hydrogen refueling hose, the system actually performs a leak test before it does any refueling. When you refuel a diesel vehicle, what you actually do is take the lid off the tank. So an operator needs to be there. If there was a problem with that and the fuel was spilling, you couldn't leave that on its own unsupervised. You can leave the hydrogen alone unsupervised, very much like you do an electric vehicle charging station. You see people plug.
You can just leave it.
Coffee. By the time they've had their coffee, their vehicle's ready to go. It's the same thing we can do with these systems.
Understood. So this is a very nice example. And then, have you deployed some of these? Do you have practical experience with this already?
Yeah. So these images here actually are 3 stations that we've delivered over the last 18 months within the UK. All of these are refueling different types of vehicles. So there's Toyota Mirais, there are buses, some are refueling some freight vehicles. The important thing to note with these systems, all of these sites operate with absolutely no cooling. So all of these operate with ambient refueling protocols, and they're in place and they're working. They accept that they'll take a slower refueling time to lose the energy and the cost burden of the cooling. So this is maybe one extreme where there's absolutely no cooling. For a lot of stations, you will need some cooling, but it's what's the appropriate level of cooling that you need.
And then Toyota Mirai, for example, to fill that one, how long would that take with these kind of stations?
So again, that's very dependent on the ambient conditions. But we would generally give a window somewhere between 15 to 30 minutes, depending on the ambient temperatures.
Understood.
And that's why we say, if you've got a fleet of 1 or 2 vehicles, you may not need cooling. If you're the motorway service station, you probably do need some cooling, but you don't need hundreds and hundreds of kilowatts. You maybe need 20 or 30 kilowatts to bring that refueling down to 3 or 4 minutes.
Yeah. So Sam, actually one point I also think that's very important is, when I started in this industry, they always said every hydrogen refueling station costs at least $1 million, if not 2 million, whatever, pounds, dollars, euros. And the way these look, do they cost that much? Are they much less expensive?
So these are the smaller end of the scale, and they are less expensive than that.
Yeah. Okay.
It is true that the hydrogen technology we're looking at has an expense to it. It's very highly engineered, high pressure process equipment. I think our responsibility as manufacturers of systems and installers of systems is to minimize that capex cost. But I think actually more importantly, it's to minimize the ongoing energy and maintenance costs. So every cost that we pass on, whether that's maintenance or energy, ultimately makes a kilogram of hydrogen more expensive, and that gets in the way of people buying hydrogen vehicles. So what we exist to do is to minimize the ongoing costs, so the operators can be more efficient and the price of hydrogen can come down.
Okay, well, that's a very nice statement. Thank you, Sam. And I think that kind of brings it all together. Like, we've learned about these complex tables, but, also the consideration of what you said, that only to compress what you need and only to cool what you need. Sam, just to get this around, what's the outlook you can give me here? So you have installed some of these systems. What are your plans for the future, and how do you see these things developing?
So we see hydrogen as an absolutely key player in the transition to a zero carbon future. What we're seeing in the industry is it's definitely the industrial users, the freight, the haulage, all the larger vehicle, be that a refuse lorry or a tractor. Also the construction sector. So think of dumper trucks and diggers. The reason for that is they are using a lot more energy than a car is. Cars actually can be transitioned to battery electric quite well. And I think it's worth being honest about that and saying that's a good solution. So we see the industrial sector and the haulage and the heavy transport sector being the first movers, and that's where we're deploying our resource and our energy at the moment. What that will do is establish a network of refueling and a network of infrastructure. And I think that's when you'll see personal mobility really start to gain traction, because there'll be a network of refueling stations that they can use, and that will lead to the smaller stations that start popping up. But we see huge demand, especially in the heavy sectors.
Right. Okay. Well, that's great. I mean, I think that's a bright future to look forward to, especially also given that this is a chance of creating a, let's say, more sustainable, renewable system of transportation and energy use. Sam, thank you very much for sharing this and for teaching us what J260, did I get it right? Is it? Oh,
J2601.
Oh my God, I still got to practice. Anyway, for that, we have the experts like you. Well, I'd like to say at this point, thank you to our viewers for watching. I hope we've all understood something here. If you like this, give us a like. And if you're looking to get into contact with people like Sam or companies like Fuel Cell Systems, come over to hyfindr.com, where we have lots of things that are related to the hydrogen industry. I can help this industry grow. So thank you very much for watching. Thank you, Sam, for doing this with us. And
thank you for having me.
You all a wonderful day. Thank you.